All right, so here we go. Today's video, we're going to be learning about angular acceleration. All right, so in the last video, we learned about angular velocity, and we learned that in the same way that you can measure velocity in meters per second, linear velocity in meters per second, similarly, we can measure angular velocity in radians per second. Okay, we're measuring the angle that something goes through per unit time. All right, similarly, in the same way that an object's linear velocity can change, an object's angular velocity can change. And when that happens, the object is accelerating, in this case, angularly accelerating. I don't know if that's a word. So anyway, learning targets. So you should understand the terms angular velocity and angular acceleration. You should understand that, like linear quantities, angular quantities are vectors, and so we got to keep track of our positives and negatives. Remember, we're just basically going to do that by means of counterclockwise is positive, clockwise is negative. You should be able to solve problems dealing with angular acceleration. There are going to be a gazillion equations this chapter, so buckle up. Is that a thing people say? All right, and then finally, you should be able to use jumper equations to convert between linear and angular quantities. All right, so here we go. All right, so one of the ideas we learned about this year early on was the idea of instantaneous velocity, right? How quickly an object was moving at a given instant and the direction. And we've always talked about linear velocity, which measures how fast the object is moving in meters per second at a given moment, right? Like, maybe you throw a ball at 40 meters a second. That's how fast the ball is moving at the instant you let go of it. Also, if you can throw a ball that fast, you should be a professional baseball pitcher person. All right? When we're talking about circular motion, that velocity we usually call tangential velocity. I mentioned this in the last video, because if your thing is moving in a circle, then at any given instant, the velocity is tangent to the circle. Okay? So this chapter, we're going to be talking about instantaneous angular velocity. Okay? So if you imagine a car speeding up, as it speeds up, the wheels spin, the wheels turn, I guess I could say, faster and faster and faster as the car's linear velocity gets faster and faster, right? And so how fast the object is spinning in radians per second at a given moment is called instantaneous angular velocity. And again, we're going to call that Greek letter omega. Last video, we really focused on average angular velocity, right? Where we had, usually our objects were turning at a constant rate, and so the angular velocity was the same as the average. All right, so this time we're going to talk about what happens if this angular velocity is changing, okay? And so we'll have, a starting angular velocity and ending angular velocity, as in initial and final angular velocities. And because there is here a change in angular velocity, we're going to have to deal with the idea of acceleration. Okay, so, oops. Last semester, we learned about linear acceleration, right? We used A to represent acceleration. That was a measure of how quickly the object's velocity was changing. Usually how quickly the object sped up or slowed down, right? Occasionally, how quickly it turned. And so, if we're going in a circle, we're going to call that tangential acceleration, right? So if you've got a car driving around a track and speeding up, then these arrows get longer and longer to indicate the velocity getting bigger and bigger and bigger. That's called tangential acceleration. All right. Now keep in mind there's also going to be centripetal acceleration, right? Because you have to have a force towards the center. Anyways, I'm getting way off topic already. So long story short, acceleration, as we've learned so far, basically is a reference to a change in velocity, usually a change in speed, and we can use this this equation to calculate linear or tangential acceleration. All right. Similarly, if how quickly something is spinning changes, then we can calculate the angular acceleration. All right. So to calculate angular acceleration, instead of finding the change in linear velocity per unit time, we find the change in angular velocity per unit time. All right, the symbols we use here are, we're just going to use, lowercase letter a for regular acceleration, and we use the lowercase Greek letter alpha for angular acceleration, okay? When I type it, sometimes it's a little tough to tell what it is. The big thing that is the giveaway is it's got a little tail on the top also, okay? So, regular a is acceleration, Greek letter alpha is angular acceleration, okay? And just like before, there is a jumper equation that allows us to convert between linear and angular quantity. So our linear acceleration is equal to our angular acceleration times the radius. Okay? So there you go. Boop. All right. So using these jumper equations, you can see that all of the equations that we learned that first chapter have a corresponding angular quantity. Right? Or angular equation, rather. Okay? In other words, if I divide this by radius, and divide this by radius, and divide this by radius, it gives me this equation. All right? And similarly, you could do some similar algebra, just dividing here, divide by r to get this guy. Here, you divide by r squared to get this guy. Divide by r, divide by r. Okay? So anyway, basically, every equation that we learned that first chapter of the year, we've now got an angular counterpart for it, okay? So you can see there's a lot of equations here. Just on the screen alone, there's 10 equations. Plus, you've got 3 jumper equations to work with, right? You've got delta x equals delta theta times r. You've got any kind of linear velocity equals any kind of angular velocity times radius. You've got a equals alpha r, okay? So these 13 equations, combined with the fact that we can convert rotations to radians to degrees and inches to meters and minutes to seconds, there's a lot going on here, all right? So really the best way to do this is, let's see some examples, all right? So the carousel at Comerica Park has a radius. These numbers are totally made up, so please don't quote me on these. All right, so let's suppose the Comerica Park carousel has a radius of 3.5 meters. I'm going to start by writing stuff down. Radius is 3.5 meters. The ride accelerates from rest, so that means that my initial linear velocity is 0 and my initial angular velocity is 0, as in it's not spinning and no part of it is moving. All right. It takes 4.5 seconds to get a maximum frequency, so that means that our frequency final, right? Our initial frequency was 0, right? I guess I could write that too, right? Our final frequency is 0.05 hertz, and we're trying to find the angular acceleration. Well, so to find the angular acceleration is omega f minus omega I over t, right? So remember, there is an intrinsic connection between frequency and angular velocity, okay? So, I don't know, some books give an equation. Some books give you this as an equation, which I don't love. It works, but in my mind, that's just another equation to memorize. To me, it's just dimensional analysis. It's just converting, because what is a hertz? So if we've got 0.05 hertz, that's the same as 0.05 rotations per second, right? Oh, let's see. I know that one rotation is the same as 2 pi radians, right? So that gives us 0.314 radians per second. Okay? So now I know my final angular velocity, my initial angular velocity, and my time. And I ought to be able to plug those in to this equation here to find the angular acceleration to get that answer. Do I believe that? I think so. Cool. Sorry. All right. Notice the units here are radians per second squared, right? Instead of meters per second squared for linear, now we're talking radians per second squared. So this means, here's what this means. Every second, the angular velocity increases by 0.7 radians per second. Okay. All right. Let's see. Next, it says, through what angle will the ride turn in the time it takes to achieve this highest speed? So here, it doesn't really give you a ton of restrictions in terms of the units. We just want to find the angle that it turns through. So I guess we're looking for delta theta, right? So here's what I'm looking at. I'm looking at the fact that, well, we know everything. So really, you can pick any of them. You can do delta theta equals 1/2 alpha t squared plus omega I times t, right? Because we know our alpha, because we just found it. We know all that other stuff. You can do this guy. This is probably the one I would use. If you really wanted to, you could use this guy. Okay? Because we know all of those values. So this should just be plug and chug, right? So grab your calculatrix, try those. My suggestion is try 2 or 3 of them, and make sure that you get 0.707 radians per radians. Sorry. Now I'm nervous about that. All right. Sorry about that. Yeah, we're good. Freaked myself out for a second. Okay, so where were we at? All right. So anyway, so that's that. Let's see. Let's see. What tangential velocity will a rider at the outer edge of the ride reach? So tangential velocity wants the linear velocity. And we're talking about what velocity they'll reach. So we're looking for VF. So to find VF, we can just do omega F times R, right? Notice, almost all of the quantities that we'd found so far were angular. So I ought to be able to just convert one of those angular quantities to a linear quantity. So let's see, our final angular velocity was 0.314 radians per second. The outer edge of the ride, what was our radius again? I know I wrote it down here somewhere. 3.5 meters. So times 3.5 meters, that's our conversion between meters and radians, right? Anytime you multiply by r, that's what you're really doing. And so that ought to give you, hopefully, our answer of, 1.1 meters a second. All right? I guess we could, if we wanted to, at this point, find our centripetal acceleration at that point. But that is not what we are studying right now. So there you go. All right, let's see. Let's do another one. All right, so this time we've got a motorcycle that is driving at 60 miles per hour. I'm trying to make this little box go away and failing. There we go. All right, so let's see. 60 miles per hour is the same as 26.8 meters per second. I will leave that up to you to do the conversion. So here are the things that we know. We know that our initial velocity is 26.8 meters per second. We know our final velocity is 0 and that it takes a time of 8 seconds to accomplish that task. Now, the tires have a radius of 0.35 meters. How many times will the tires rotate before the bike stops? All right, so there is a gabillion, are a gabillion different ways to do this. Here's my recommendation. We're trying to find how many times the tires will rotate. So we're looking for change in theta, right? Number of rotations is the same as an angle. 2 rotations would be 720 degrees, right? So we're trying to find the change in theta. The linear connection there is delta x. So you got a couple options. Option 1 would be to convert all of these guys individually to angular quantities and then calculate it. My recommendation is this. Almost all the, well, in fact, not even almost, literally all of the numbers we've been given here are linear quantities. So let's work using our linear equations, then use a jumper at the end. So, in other words, I think I can use this stuff here to figure out delta x. Right? So plug in your numbers. You're going to get 13.4 times 8. That gives you a number. 13.4 times 8. So your displacement, linear displacement, is 107.2 meters. Okay? So now we want to find our delta theta. And specifically, we want it in rotations. So option 1, use a jumper. and then convert radians to rotations. So you're going to do, delta x over r. So 107.2 meters over 0.35 meters per radian. So divide by 0.35, that gives you 306.3 radians. And then convert that to rotations. So divide that by 2 pi to get 48.7 rotations. Or we could have just taken this and divided it by the circumference. Okay? Uh-oh. Rounding. All right. All right, and then it wants the angular acceleration of the tires. Okay, so I guess I would say let's find the linear acceleration and then jumper it. So acceleration is Vf minus Vi over t. So we know our Vf, we know our Vi, we know our t. So looks like we're going to get an acceleration of negative 3.35 meters per second squared. So then alpha is a over r, which is 3.35 meters per second squared over 0.35 meters per radian. And you get 9.57 radians per second squared. Okay. So really, this section is not, oh, I'm sorry, I forgot my negatives, didn't I? I had the negative here, right? Negative, but then I forgot to put it here and here. All right, so really this section is largely just about learning those equations. There's so many of them. So really this slide here, which I will now embiggen so that you can see the whole thing, that's your jam right there, okay? You gotta be able to work with those 13 equations. All right? Let me clear it up. All right. Okay, happy angular motioning.